This video explores the topic of current transformers within the framework of the European project, titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. Current transformers, also referred to as CTs, are a type of current transducer that operate based on current reduction. They provide galvanic isolation between the input and output terminals, ensuring safe signal transfer. The power dissipated in a CT is limited to the iron and copper losses within the transformer. As illustrated, the basic schematic of a current transformer highlights the galvanic isolation between the primary and secondary windings. The voltage and current relationships, expressed in terms of the winding turns ratio, can be represented as indicated on the slide. As shown in the diagram, in an ideal CT, the primary winding is connected in series with the line carrying the current to be measured, while the secondary winding is connected to the measuring instrument. The transformer provides perfect galvanic isolation between the primary and secondary sides, meaning no direct electrical connection exists between them. According to the ideal transformer equations, the ratio of primary to secondary currents is inversely proportional to the ratio of the number of turns. Therefore, the current on the secondary side is scaled down according to the turns ratio, allowing accurate measurement with standard instruments while keeping power losses negligible. Here we can see a very important safety consideration when working with current transformers. In an ideal CT, the secondary current is given by I2 equals 1 over KT times I1, where KT is much greater than 1. This means that if the secondary circuit is accidentally left open, the transformer will try to maintain the magnetic balance by generating a very high secondary voltage, much higher than the primary voltage. This high voltage can be extremely dangerous. It can damage the CT itself, cause electric arcs, and even lead to an explosion. For this reason, the secondary of a current transformer must never be left open. Before disconnecting any measuring instruments, the secondary should always be short-circuited to ensure safe operation. A real current transformer behaves like a practical, non-ideal transformer. Its performance can be analyzed by studying the equivalent circuit representation of the transformer. To analyze the vector diagram, let's start by defining the flow phi and the secondary current I2. In this sense, it can be said that the secondary current is drawn from the primary side, denoted as I12. Here we're looking at the vector diagram of a current transformer. On the left, you can see the ideal case. The secondary current, when referred to the primary side, perfectly cancels out the primary current. So I1 2 inches equals negative KT times I2, and everything lines up neatly. On the right, we move to the real court. Here, part of the primary current is used to magnetize the core, that's the excitation current, I0. Because of this, the total primary current I1 isn't perfectly opposite to the secondary current anymore. What about that little angle between I1 and I12? That's what gives us the ratio and phase errors, the practical limitations that every real CT has. Here we can see how measurement errors appear in a real current transformer. The red vector represents the ideal current referred to the primary I12 equals minus KT times I2, while the orange one is the actual primary current I1. The small angle epsilon between them is called the phase or angle error. It shows that the secondary current isn't perfectly in phase opposition with the primary. This phase shift, together with a slight magnitude difference, leads to ratio and phase errors in CT measurements. Here we see the ratio error in a real current transformer. The red vector I12 equals negative KT times I2 represents the ideal secondary current referred to the primary side, while the orange vector I1 shows the actual primary current. The difference in their magnitudes gives the ratio error, meaning the actual transformation ratio isn't exactly equal to the nominal one. This happens because part of the primary current is used to magnetize the core, so the actual coefficient slightly deviates from the theoretical value. Alternatively, considering the angle theta, it is also possible to rewrite the previous relationships in the shown form. In order to reduce errors, it is necessary to reduce the no-load current, which firstly depends on the core of the transformer, and secondly depends on the number of turns. One possible fix to the former issue is to design an oversized core. The ratio error is naturally always negative, and by appropriately considering the rated ratio, it can be forced to 0 for a given current. On the contrary, the angle error is always positive. Now let us consider ZB as the load of the court. It can be said that the lower the no-load current, the lower the measurement errors. For this reason, in the ideal case, the CT should work in a short-circuited state. ZB is called burden, the maximum apparent power of the external circuit that can be connected to the secondary circuit, for which the CT is guaranteed to work in its accuracy class. The accuracy class is a synthetic parameter giving the limits of the maximum phase and ratio errors. The main limits of the CT are related to the limited bandwidth, the nonlinear behavior, and the saturation effect due to the presence of the magnetic core. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.